Okay, for the online students, can you hear me? Well, let me see. Yes, okay, good. So, so this morning we spent some time on the IRA, and quite smooth, So make sure that next time you come, next week, you come, you have to do it exactly at 9:30, because otherwise you will your working time will be deducted, So be careful. Okay, so this is tutorial number 2. So I think I have recorded. Hopefully everything should be fine. So later on, as usual, I will send you the link. So you can review it if you want. Today I have to stand here because I cannot do much here. Because the mic is here. If I far away from that, you can hear, then the online student will be not very clear. So most of the time I will talk to the mic. So please be patient. So okay, so this is tutorial number 2. So this course is very heavy. You see that every week we have one. Even the first week we have tutorial 1. So very, very intensive. Okay, so let's look at question number 1. So you see that you have the algo, you have good idea. How can you implement that and then show it to your supervisor or show it to your colleagues, right? So you have to use the pseudocode to do it. In this course, we use pseudocode. I think in the old days, we used what we call the flow chart. Now we have changed it to pseudocode. The pseudocode has no very fixed format. So you can see that. So you watch the video, you'll know that not very precise. Because it's pseudocode. It's not like the C language or the Python language, very precise. You see, you put into the interpreter or the compiler, they know that you are wrong or you are right? They can execute. But here is not really that precise. But you have to tell us what you want to do. Okay, so look at the question. So it's very simple. You have an array. The array may be very big, 100 elements can hold. But the active element may be only 10 of them. So how do we call this 10? 10 elements are stored there. This one is called S dot last. If the array is called A, then it's A dot last. Okay. So so we don't go to all the way to 100, although we have 100 spaces, or 100 elements to store, but we only use about 10 of them, for active array. So we would like to sum these 10 elements together. What will be the one? How do you do it? So of course, this is the first question. Normally very simple, right? Yes. Huh?
Not showing the slide.
Oh, so sorry. Oh, I see. So you have to tell me. So thank you. Because I have too many things to take care. So once you find something I miss, let me know. Okay. So so now should be better, right? should be better. Yeah. Okay, so you have m elements. M is like the 10 we have. Although the exact size of the array may be very, very big. Yeah. So we don't care about that. So we good enough to hold these m elements here. So how do we do it? I think we all know that. Look at the pseudocode. The pseudocode, your input output is just to help me to understand your idea. So we say that, oh yeah, you have the input. The input is the array. And so you see that the size may be very big, but we only use m elements there. So the output will be total. Surely this one will be the sum of these m elements, right? So how do we do it? We'll give the name there. Call maybe called algo sum, yeah, or sum. The title of the algo is called sum. So the parameter is s. S is the array. Yeah, so we need the array in order to do it. So at the very beginning, we set it equal to 0. You set it equal to 0, right? Then we use a for loop. So you look at it. We use the for loop from 1 up to m. So we don't need to know, because this question tells you that we want to sum the first m elements, right? So you know that the for loop will be from 1 up to m. Then the total will be sum them together. So you see that the indentation here. The indentation here tells you that, oh yeah, this one will sum it is repeat again and again m times. At the end, total will hold the sum of them. At the very beginning is 0. Later on, you hold the total of that. And we return this single value here. Total is the result, right? It's a single value. So normally, like if you are familiar with C and other language like Pascal, you know that function can only return one item. I can show you one item. Maybe this item can contain many things. Maybe it's an array of 100 elements. Then you will receive 100 elements. But when I throw it to you, it's only one array or one item. So this is a very common for the languages. So most of the language will be like this. When you return one element. So later on, we will talk about that and how do we return more than one. So if you have many things, yeah, one way is to tie them together into an array, into some other things, and then we return it. Or we use another method. Yeah, it will be introduced in your next question. Yeah. So this one, I think you have to know the structure of that. Normally, you tell me that what will be the input, what will be the output. Yeah. Although this one is actually not part of the algo, it's just to inform me when I mark your algo, it's very painful. You see, I'm not that smart as you. I am maybe go to this direction. You are talking about this direction. Very difficult. How do we align together? Once we align together, you have some advantage, right? I understand what you are doing. You will get marks, right? You see, I give you marks, right? Yeah. So you have to align your thinking with my thinking, right? So the best way is to tell me more. You have to put in some comment. Yeah. So you see that the comment is double slash here. Is a comment. So if you think that, oh, that will be useful for me to understand your thinking, your algo, so put it in, yeah. Because although you think that it's very simple, yeah, sometimes I may miss it, yeah. So if you say that, oh yeah, this is very important, yeah. So you put the comment there, so I know what you are doing. So will inform me. So basically align our thinking. Once I know what you are doing, I will appreciate that. Yeah, give you marks. Correct. This one is also correct. Yeah, like that. So you help me, I can help you. I think we have to align together. Yeah. Okay. So this one, any problem for the E-class student? Very simple, right? Very simple. So you can try other means to do it. Find the maximum, find the minimum, whatever. Yeah, you have to try it. Yeah. If you think that this is very difficult, it's very difficult. Right? Yeah. So you have to remember that when you use this return statement, you return one item. This item may be one table. You fold one table, then this 4 guy will go to the other side, right? But one item. This is the key. Any questions here? No. Okay. For the online student, it's your turn. You can tell me the question full check, or you can turn on your mic and speak to everyone. But sometimes the audio quality is not very good, either very loud or very soft. Yeah, so sometimes I may need you to explain again. Okay. There are no fixed formats for this pseudocode. Sometimes we say that for I equals 1 to m, do something. Yeah, it's also fine. You have to do like that. But basically, I'm using the C type of format, like the C language. Yeah, so it's like that. But I don't use the semicolon. So, but you use semicolon also fine. I will not deduct marks here. Just make me clear. You use the curly parentheses to so-called enhance the readability. That's fine. That's fine. Okay, good habit. No problem. As long as I understand what you mean, understand your thinking, then you will gain from that. Okay. I don't see any question here. So we move on to the next one. The next one, so here, why an algo that outputs the smallest value and the largest value in an array, which has m unique elements. Yeah, so very similar to the previous one, but this time we have to return 2 things, right? The maximum and the minimum. You cannot return maximum, minimum. Yeah, so like that you cannot. Yeah, so the input will be S. There is the array. The output will be the maximum and the minimum, or the smallest and the largest. So the remark here is we cannot return these 2 things. So this is not acceptable. Return smallest, largest. There's no such. We don't use this return. You cannot say that. Oh yeah, I have 2 things. I return the first one and also return the second one. So this is not acceptable in this course here. Okay. So how do we do it? How do we do it? Then you have to use what we call kind of define a space, define a variable, a global variable for this smallest and also the largest as a kind of a parameter at the very beginning. It's like that. You see that the program name is the algo is called smaller, small, large. So the name you can call it test or whatever. So S will be the first array, but you reserve 2 variable for that, smallest and largest. Basically, is 2 seats here, just like your table. You have many seats. You reserve these 2, one for the smallest, one for the largest. So kind of like global variable, like a global variable in C. In procedure in Pascal will be also like this here. You reserve these 2 spaces for the largest and the smallest. Okay, so the space there at the very beginning, you don't have anything there. So later on, because this one here is this algo is part of a big program. So the big program, you know that I have reserved the smallest. Later on, after the execution of that, I will go to the smallest to find this value and go to the largest, the seed here to find the largest and the small value. So we do it like this. But we don't return two things. That's what we have mentioned here. Okay, so the algo is very simple. First, we say that the first element is the smallest value and the largest value. We ask the S1 to sit here and sit there. Okay, so we start to test from the second element up to the last element, all right? So we test it. If it's smaller than the smallest value, then this is the new smallest value. Please sit there. So this one is the first if statement. And also we test the value. If this one is even bigger than the current largest, then please sit there. This is the largest, the new largest. Yeah. So we do it is a loop. We do it for all the elements. Yeah, from 2 for the index 2 up to m. So after the execution, the smallest really sitting there, the largest also placing this speed here. So we have find it. Then we don't need to return because we have set aside 2 spaces for them. One is called smallest and largest. So when the bigger program, the main program, whatever, to call this one, you should know how to collect this smallest and the largest after the execution of this algo. So this is how we operate that. Is okay? Questions? Yes.
That means that by programming this, you must already plan to actually put it as set it as a global variable at the top.
Yeah. So you have to define this one here. In your C, you have to define this one here. Later on, you will go there to do it. So we don't care about the main program, how do they handle it. We are focusing on the procedure, this particular function. So basically, we still have a space for that. It's called smallest, and the other one called largest. But we cannot use, say that return this one here. But you may say that, oh yeah, I can create an array, 2-element array. The smallest will be the first element. The next one will be this one. I return this array back to the main program. That's acceptable. That's acceptable. On the paper, it's okay. So it's nothing wrong. Yeah, but you can do it like this. But the easiest way is like this. This is how we do it here. Yeah. It doesn't mean that your programming is like that. Yeah. So there's so many possibilities, so many variations. Yeah. So you have to pity me when I mark your paper. So everyone will be different, right? We emphasize that is student-centric, right? So your answer is different from his answer. His answer is different from their answers, right? So I have only one guy, you see. Very difficult. So you have to help me to align it. Yeah. So so follow this instruction is a good habit. Of course, your way may be also fine. Yeah. There are many possible answers. Sometimes when I mark your paper, and then after 1 hour, I think, wow, still possible. Then I will go back to click, you see, and then find your paper and then redo it. So last time, yeah. So last time, the last question, I think the examiner has marked it 3 times. Yeah, you think that, oh, this is still possible, and then go back to redo for 200 students. And then after 2 days, I'll say, oh, yeah, this one probably not. Yeah. Then you go back to that. You mark it a few times. Yeah. So you see that how difficult it is. Yeah. So if you can help me to align yourself, your thinking with my understanding, then you will definitely will help me and then help yourself. Yeah. Okay. So any question about online student? Do you see any question here? Yeah, I don't see any question here. So I go to the next one. How about that? Okay, so this one is an array. It has the element S1, S2 up to Sn. Okay, it has the property that is non-decreasing. Always bigger or equal. Yeah, to that. All the elements will be like that. So we will write an algo to insert one more element to it. To insert one more element at that. Maybe at the very beginning you have only 10 elements. Now you insert one more there. Once you insert, then you have 11 elements, right? And also you have to maintain this property. So the first one is smaller than or equal to number 2. Number 2 is smaller than or equal to number 3 and something like that. Non-decreasing order. So okay. So you have to maintain this one. How do we do it? Yeah, there are many ways to do it. Yeah, even the tutorial instructor, they have different version of that. Yeah, so it's also quite easy to do it, but many ways to do it. Yeah. Okay, so you know that we insert one there. So in language, in C language, if you define the array is 10 elements, and then you put 10 elements there, you cannot increase it to 11 elements, right? But here we assume that the array is very big, maybe 1,000 elements. Yeah, but we use about 10 of them. So still a lot of space to expand. Don't argue with me, say that, yeah, so cannot, let's see, cannot. So I would like to mention that here we assume that the array is very big. We use only a small part of it. Because this one is to balance the binary search tree. Yeah, so later on. Yeah, so we just modify to put into this kind of environment. Yeah, but don't worry about that. At that time you learn it. Yeah, so look at this one here. So how do we do it? So the first one is the input. You have the S. S is the array with n elements, right? So, and now you insert a value to it. The value is called x. After inserting x there, you have n plus 1 elements. N plus 1. So one thing here, the array starts from 1 up to n. So you have n elements. Sometimes it will start from 0 up to n minus 1. In C, it's like that. Everything starts from 0. Everything 0 and then 1. All right. This is false. This is true or something like that. So all the arrays start from 0 up to certain value. So if you have n elements, it will be from 0 up to n minus 1. Also acceptable in this course. Not necessarily start from 1 up to n. It can start from 0. You can define it. Oh yeah, the starting value is 0 up to n minus 1, and you have n elements. Possible, acceptable, correct. So you have to be careful, You have to be careful. But sometimes the answer is from the array is assumed that the index is from 0 up to n minus 1, n element. Maybe sometimes it's from 1 up to n, also n elements. Both of them are used in this course. Okay, the output will be S, will be the array S. So we will have one more element inside, and then we will maintain this property non-decreasing. Okay or not? So this is the answer. So before we do the answer, let's see the example for that. I have an example here. The example is like that, yeah. So we have the array. It has 8 elements here. So at the very beginning, the array, the big array has 8 elements, can hold 8 elements. So this is an array index here. And we would like the array initially, we store 4 values here, 2, 4, 6, 8. So 2 will be stored at S1, 4 will be stored in S2, 6 will be 3, and then 4. 5, 6, 7, 8, we don't store any value. So in this case here, this is what we call the active one here. The others, we don't care about that. Okay, so 2 will be stored at S1, 4 will be stored at S2. This one S3 and S4. So like that, we only use 4. Now we insert a value to it. The value is 7. So of course, you look at it, 7 should be insert between 6 and 8. Yeah. So but the computer has to find it. The computer is very dumb, so cannot do it. So now we define the one called S dot last. S dot last is how many active elements you have. 4 of them. So at the very beginning, the active S dot last is only 4 here. But because we add one more at the position 5, so now S dot last becomes 5. You have 5 active elements there. We put it, the inserted value here. It just to hold the space, it doesn't mean anything. Okay, so how do we do it? So S5 is now equal to X. So the X will be used to compare with the last element here, 8. If this one is smaller than that, 8 will be copy to this one here. 8 will copy to this one, but the previous value is still 8. The previous value there. Then the next one, 7 will compare to 6. So you start from this one here because you have 4 elements. So we start from number 4 and then go to number 3. Go to number 3 and see whether 7 is smaller than that. That one is not true. When it is not true, you stop. You stop. You don't need to do it. So in this case here, the value of I is equal to 4. You have to add equal to 3 because this is number 3, right? Now you add 1 to it and then put the 7 here. You add 1 to it, put the 7 here. Okay, let me repeat again in a more smooth manner. At the very beginning, n dot last is equal to 4. Only 4 elements here. Now you increase the n dot last to 5 and put the X value here to hold the space. It doesn't mean anything. Okay, so now the 7 you go to compare one by one. If this one is smaller than that, then that value will go to the one next to it. Yeah, so like next to it. We keep doing that. If this one is still 8 here, then the 7 will be smaller than 8. Then this 8 will copy here. Yeah, so they're like that. Later on, we see the algo will do it. So once this condition is not true, we stop at this point and then we count it. What's the position of that? The position is 3. The position is 3. We stop. So the new value will be here. The 7 will be placed here. So now this one is with 5 elements here. So this is the example for that. Yeah. Okay, so look at the algo. Yeah. So we insert X to this array. Yeah. First of all, we have to know that how many elements are there in the S, in S. The array S dot last here will tell you that how many elements there. So in our previous example, we have 4. We have 4. S dot last is 4. So if your index is from 0 up to n minus 1, then your n dot last is still n. N dot last is basically how many elements in your array. How many elements in your array? Whether you start from 1 up to n or 0 up to n minus 1, the answer is n. You have n elements inside it. Okay, so you have 4. Now you increase it by 1 because you have to add 1 more elements there, right? So you put the x at the last position, this one here. Okay, so we will do the checking at the position n. N is 4, right? So we will see that if x is smaller than the array value and I is greater than 0, then you will you see that you will move this Si to S plus 1. So move to the next one. You keep doing that, and also I will be deduct by 1, reduced by 1 here. So this one is an array. You see that these 2 lines here are indent. They are at the same level. So the while loop here will do this 2 and come back to check this condition again and come back again. So these 2 will be one group here. Okay. After that, you see that you start at the I, but you increase it by 1, and Si plus 1 is equal to x. So you go home, you can try it. Yeah. If you cannot see it, you can see my example there. At the very beginning, we have 4. We put the last one, 7 here. So the new value will compare with 8. Is it smaller than this guy? Oh, yes. Then this one will move to the next. We'll copy this one to the next. You count to this one. If this one is smaller than this one, if it's true, then this one will move to the next one. But this one is not true, we stop. Then we have to record the position of that at the 3. Then we will put the new 7, the insert the value here. Then that will be the correct one. So this one is actually a bigger program in the binary search tree. How do you shift up, shift down, all this? We need this kind of algo. But we don't touch that now. I just ask you because, of course, this one may not be optimized, right? Yeah. So there are many ways to do it, but at that time we'll use this algo. You may have similar algo. You can trace it, use some example. If it works, then likely it will be correct. Yes. Any? No. Okay. So how about the online student? Do you see that? So I will send you the link later on. You trace it, see whether you can understand it. The algo is here. Let me see the remark at the end. You may assume that the size of the array is very big, as what I have told you lah. It's very you add 1 more there. So the active value will not be affected. Yeah. So we only use the first n cells to store value at the very beginning. So later on, we expand 1 more value there. It will not affect that. Yeah. We make this assumption. Yeah. Because in some language, yeah, once you define the array as 10, you cannot hold 11 elements there. That's the problem. So we assume that we don't have this problem. Questions? Legs. When you watch the videos, always legs, right? Yeah. So that one is by Prof. Lawrence. This one by low chopping. Yeah, low chopping. Okay, so this one is like the growth rate. Yeah, the growth rate. Yeah. So in your mind, you know that you have given a few functions here. Which one is the fastest? Yeah. The fast one is n factorial or n factorial. N factorial will be the fastest. And then which one is the slowest? The log n, log n is slowest. Yeah, normally. Of course, the constant is not a constant is the smallest, never increase, right? So if you find that if we put one is like 2, say like that, or 5, yeah, then of course that one is probably smaller, the slowest here, because if it's 5, it will be 5 forever. It will not increase the value. Log n still increase slowly, right? So you will see that out of this group here, this one surely will be the smallest. Now, why? Even the power here is 10, but you see that using the logarithm algo, this power can put it here, and 5 times 10 is 50. So this one basically is coefficient 50 times the log. LG is log base 2, that one here. So this one is still a log here. Log, if you don't see it, the constant, then this one is the slowest. It's okay? So we'll put down the answer for the first one, from the lowest to the highest. Lowest is the log, this one here. So it's okay. Next. So next is this guy or this guy or this guy. Now, so compare these two. This one is 4 to the power n, right? This one here is 4 to the power n. This one is 3 to the power n. Comparing these two, 4 to the power n should be faster, right? And 3 to the power n is slower. But you are not very sure that this n to the power 4 and the 4 to the power n, which one is faster? You are not supposed to use the calculator. You use the calculator, of course, you know the answer. Now, how do we know that? So you watch the video, you know that. If we take the log, okay, first of all, this one is dominated by n to the power 4. So the other term are lower, right? We don't care, because we assume that n is very large. N is not 1 or 2, is 1 million, 1 billion, that kind of order, right? So very, very big, very, very big. We don't care about this one, because when you compare them, you have 3 terms here. The first term is the dominant term. Okay, so you take the log of this one here. Take the log of this one. So when you take the log, okay, so when you take the log is equal to n log 4. So it's equal to 2n. 2n, So this one is 2n. So how about the other one? N to the power 4. I cannot see it, so light. Where is it? Here. N to the power 4. You take the log is 4 log n. So you compare that. The upper one is 2n. The lower one is 4 log n. This one is linear proportional to n. This one. This one is linear proportional to n. This one is log n. Of course, a linear proportional to n is faster. if you compare that this one is faster, then this one should be faster than that. Because if A greater than B, they are both positive. Then log A is greater than log B. So they have maintained this property. You can try it. If you have something like that, yeah, this one, A is greater than B. You take the log on both sides, whether you are base 2 or base 10 or whatever, doesn't matter. Then if you, after that, you compare that, if log A is greater than log B, then A should be greater than B. So you take the log. Now we take the log, we know that this guy n to the power 4 is smaller, slower than this one. So that will be the next answer, right? N log n, n log n is here. So n log n is the next one. Then after n log n is, we can understand log n here. Next one is log n, n log n is here. So now we compare these two. So when you compare this one, the n to the power 4 will be the next. So I missed the n log n. N log n is the next one. Log n is the smallest side, and you times n is still less than n squared, less than all this. Yeah. So after that, now you have 2 to the power 2n and 3 to the power n. As what I have mentioned, 3 to the power n should be smaller because it's 3. The other one is 4, the value. Okay, 3 to the power n, and then 4 to the power n, and the last one will be n factorial. So this is how we do it. Of course, you use the calculator, you will see it, but you are not allowed to use the calculator at that time. Yeah, so of course you plot it, use your Excel to plot it. Of course, you know which one is faster. So okay, so remember that if you are not very sure, ask the logarithm to help. Take the logarithm on both sides, then you will see that which one is bigger. Then that one should be faster. Okay. Okay or not? Online students, do you have any questions on this one? Okay or not? Yes, okay. So today here we have 18 students. Online we were 16. Altogether 34. The total number of students in this class is 34. So all of you are here. So very happy, Okay, so now we'll move on. Let me see, 10, 11. Oh, good. So now you see that prove the following assertion here. If Fn is a big O of Gn, so that means Gn is an upper bound of Fn up to a scaling factor. Scaling factor may be called C or K or called whatever. Then Gn should be a lower bound of Fn. So this one, big O notation is an upper bound. This one is a lower bound. The other one is the big theta. Big theta is the tight bound here. Okay. Okay, so what does it mean? How to do it? The question actually is very simple. If say that I'm older than you, that means you are younger than me, right? The same story, right? No big deal. So this one is very simple, if you understand it, But mathematically, you have to put it there, So he said that this Gn is older than this guy here. That means this guy is younger than the Gn. So the same story. The same story. You think about that? So this question is very, very simple. So let's see how to do it. Okay. So what does it mean is an upper bound, a big O notation. So when n is very large, okay, so greater than some value called n naught, then Fn is upper bound by Gn, is an upper bound by that with a constant value C up to a scaling factor C here. So Fn so upper bound is called Gn. Gn is an upper bound of Fn up to a scaling factor there. That is the definition of the big O here, big O notation. So how can we say that this guy is smaller than that? Then you just move it to the other side. It implies that you move the C to the other side, then you see that Fn should be the lower bound of the Gn with the constant value, with the scaling factor, but this time it's not C, it's 1 over C, right? 1 over C. So it's the same story. So the same thing here, because this one is true, then this implies that this one is also true, right? It's also true. Because this one is true, then this one is true. But here the scaling factor is C. Here the scaling factor is 1 over C. Because we move to the other side, and C is a positive value. It doesn't matter once you move it from one side to another. There will be some changes, in that, Okay, so now we say that because from here you can see that Fn should be the lower bound of Gn. So Gn is lower bound by Fn. So this line here actually is from this line here. And this line here is from here, So exactly the same story. If this one is bigger than that, then that means the other one is smaller than that. So, right? So the idea is very simple, but how you so-called mathematically prove it, then you have to use some intelligence, to do it. So any question here? Okay, so for the online students, any questions? You are very quiet, Okay, go to the next one. Now the next one is like that. You take the log of n to the power k per c is a big theta of log n. That means upper bound by log n or lower bound by log n. So you have to prove that because this one is a tight bound here. So you have 2 steps to do it. The first one is to say that log n is an upper bound of this one. And then the second step is log n is a lower bound of that. If both of them are true, then this one should be a very tight bound, all right? Can be an upper bound, can be a lower bound. But they may be up to certain different scaling factor. The scaling factor may not be the same, but it's a constant, that's fine. Okay, so we have 2 things to do it. The first one is upper bound. The second one is lower bound. Let's do the first one here. Okay, so if n is large, n is large, say n cannot be small, right? When we talk about n, because we are talking asymptotic notation, right? So n should be very large. N is like 1 million, 1 billion, that kind of order. Okay, so k is already a positive value, right? So n to the power k must be greater than c. So c is a constant, right? Maybe 100. Then we can use different value of n. If n equal to 10 not enough, make it 100. If 100 not enough, make it 1000. All right. Surely at some point, if n is large enough, it should be greater than C. This guy should be greater than C. N large, yeah. And also we need to have another one. This one is greater than 2. Greater than 2. Why do we need that? Because later on we need that. Later on we need that. Yeah. So currently you don't see it. Currently you don't see it. Okay. So this one must be greater than C, and this one must be greater than 2. We will assume that this n to the power k must be the maximum of these two. So should be big enough, big enough. Then you can argue that, yeah, why is so like that? Because n is very large here, and k is positive. Surely it will exceed the value of C and then greater than 2. Okay, so we say that the first one, so this is C. I make it bigger, n to the power k. I replace C by n to the power k. Is right? Because it's greater than C, greater than C. So I can replace C by a bigger value. Once I put a bigger value, then it's like that, right? Then now the one is here. We have the product of 2. So now we know that n to the power k is also greater than 2. We use the green one, all right? We use the green one. So we replace this 2 by n to the power k again. This 2 here, this 2 here, we replace it by n to the power k by something bigger. This one, I already replace it by n to the power k. And later on, when we simplify it, get a 2 here. I don't like 2. So I replace this 2 by n to the power k. So after the one here, so should be n to the power k times n to the power k. At the end, you simplify it is 2k log n. So you see that after some manipulation, this expression here is smaller than k log n. Log n, greater than log n. Then the scaling factor is 2k. The scaling factor is 2k. K is a constant, right? 2k is a constant. So this one is a constant. So is upper bound by log n up to the scaling factor 2k. Can we say that? First, we replace C by n to the power k because we know that n to the power k is greater than C. Later on, we find a 2 here, and we know that this one is also greater than 2. We also replace it by n to the power k. Then we can simplify in this way. Okay, now.
The two can be any number. The two come from where?
From here, because you see that you add them together, you get a 2, right? N to the power k plus n to the power k. A plus A is equal to 2A. So 2 is from there. So that's why I have the green one, nk was greater than 2. That one is a little bit complex, yeah, so I have to use different colors. Okay, so now we say that upper bound by log n. Now we will see that we want to know that this is lower bound by log n. So we'll do it. So on the other hand, you take the log here, we ignore C. C is a positive value. So we ignore it, we don't count it. It should be greater than log nk. So after the manipulation is k log n. So you see that this expression is greater than k log n. So that means lower bound by log n with the scaling factor k here. The scaling factor k here. The previous one is the less than that with the scaling factor 2k. This one is greater than, lower bound by log n, but the scaling factor is k. So log n can be an upper bound, can be a lower bound, right? So it must be a tight bound. So that's why we conclude that combine the above arguments, we have the final result is a big theta of log n. Okay or not? The color is important, yeah. So you see that, the red one is here, the green one is here. The color is important, yeah. At first I used red, then I found that maybe this one is better. Okay or not? Think about that. Yeah. So you have to understand that theta, big theta, is an upper bound as well as a lower bound. As well as lower bound. When you try to prove it, you have to prove two steps. So at the end, you combine them together. Okay, so let me see. I thought question 6y n to the power k equal to 2. Can't hear just now. Oh, it's the same story here for n to the power k. K is a positive value. N is very, very big. The left-hand side must be greater than 2. If n is equal to 10, not enough, make it 100. 100 not enough, make it 1000. You keep increasing n, then n to the power k must be bigger than 2. So this is the argument. So we need this n to the power k greater than c. We need this n to the power k greater than 2. We assume that n to the power should be the maximum of them. If this one here, when n equal to 100 will be good enough, this one need to be 10 will be good enough, then we make it bigger, 100, n equal to 100. Surely this one will be the biggest of these two. So the argument is like that. Okay, so now any questions? Think about that, yeah. So so this one is easy lah. So Fn is equal to 2n squared plus 1. So this one is not important lah, right? So it should be actually is n squared. It should be n squared. Should be a big theta or n squared. We just do one hand side. Yeah, so bigger than. So it's like this. I think it's quite easy. How do we choose? Because we need to choose the value of n naught. We choose the value of k or c. I don't know whether I use c or k. Okay, so you see that if this one is an upper bound, then this Fn here should be less than n squared, because the n squared up to the scaling factor k here, right? This one here, the Fn must be less than or equal to n squared times scaling factor k here. Okay, so after the manipulation, we have to choose the k and the n greater than n naught, the n naught value. So you see that after that, you see that 1 is here. This one you move to the other side, then you have n squared k equal to 2. How can we greater than 1? So you have to choose the value of k. There are many choices here. Yes, there are many choices. So if k is equal to 100 and n naught is equal to 1, then this one surely correct lah. The smallest value is when k is equal to 3, right? 3 minus 2 is 1. And then this n squared, if is greater than n naught, greater than 1. If n is greater than 1, also greater than 1. So one possible value is this one. We can choose k to be 3, and then the smallest value of n to be 1. Then this inequality will be correct, right? So this one is 1, and then we say that we conclude that this is true. But this is not the only choice. There are many choices for K and N naught. You can choose K to be 4 and N naught to be 1. Then this inequality is also true. So this is also true. So as long as we find a pair, make this one happen, then it's correct. You can choose K equal to 3, N naught equal to 5. Yeah, also can. Many choices. It's quite loose, that part. As long as you find it, it's okay. So basically it's bound by n squared. So from here you can see that. Any questions? So you have to understand this big O notation, the asymptotic notation. Yeah, what does it mean? It means that if this one is an big O of n squared, that means this Fn should be smaller than n squared times the constant. This constant is the scaling factor, I call it. Then if you can find a pair of value, the K and the N naught, then if this one is true, then this is correct. Yeah, there are many possible ways to do it. If I say that I'm older than you, so if I'm 50 years old, I'm 60 years old, I'm 70 years old, all of them are correct, right? Yes. No. You are using the one. Okay, the choice are not unique, so I think this one is okay. Okay, go to the second part. I think is more interesting, yeah, because they are the same. Fn is equal to 2 to the power n plus 2. Prove that this one is a big O of 2n. So the Fn is smaller than 2 to the power n times k. Right? Times k. So you see that 2 to the power n plus 2 actually is 4 times 2 to the power n. Because the exponent, you can split it into 2 parts here. And by definition, if this one is big O of 2n, should be 2n times 2k. Times k here, sorry, times k here. So you see that what's the value of k? Because 2n cancel out, actually k will determine whether it's greater than 4. You can choose it to be 4, then it's just big enough. If you can choose k to be 5, that's fine. You can choose k to be 100, also greater than 4. So there are many choices. The smallest value is when n is equal to 4, n naught is equal to 1. Then this one is true. Okay, so as what I mentioned, this is not the only choice. You can choose the other value of k. You can choose k to be 5, n naught to be 1. So in this case here, this is also correct. So we conclude that this one is true. If you choose k to be greater than or equal to 4 or 5, whatever, up to you. N is greater than 1 here, n naught is greater than or equal to 1, then this is true. Then there are many choices. Any questions here? Online students, your turn. No. Okay, any questions you can answer? You can ask, yeah. Okay, it's almost time. Later on, I talk to you here. So once I close it, yeah, because so many students are looking at me, they say, yeah, I'm so nervous now. Any questions here? Okay, online student, your turn. Okay, so almost time. I think I need to close it. So any question, you send me an email. I try to help you. And once I receive the link, like last week, I will send you the link. Yeah, then you can review it if you want. So I close this one at this time. Thank you very much. Thank you. Cannot, how come, huh?